Thanks everyone for joining the webinar Newton versus LLMs, the case for physical AI. Archetype is a physical AI company that's helping make sense of the physical world through the lens of sensor data. My name is Aristo Chang, and I'm on the product marketing team here. We're excited to be joined by Laura and Lucas, who will walk us through why the physical world needs a new type of AI and what we're doing specifically at Archetype in order to solve that. So before we go ahead and get started, we're gonna cover a couple housekeeping items. So one is we will be recording the session and we will share it over email. So keep an eye out for that over the next day or so. And two, as you have questions throughout the webinar, please feel free to submit them at any point, and we'll cover them all at the end, or as many as we can at the end. Please use the Q&A feature to submit questions. Note that there is a chat. It is something that we will not be monitoring. So please, as you have questions, use the Q&A feature. Okay, and so for a quick recap of the agenda, we'll start with the case for physical AI, where we'll hear more about the challenges of solving AI in the physical world and how that's different from other language-based use cases, and what we're doing with Newton in order to solve that. We'll then transition to hear more about the Archetype platform and how we're actually taking Newton and applying it to real-world use cases. And then we'll end with a live Q&A where we'll try to go through as many questions as we can. And for our speakers today, we're excited to be joined by Laura Galindez, an AI research scientist. Laura's on our research and development team that is behind Newton, our AI foundation model. And we have Lucas Giannini, who is our AI solution specialist. Lucas is on our solutions engineering team and works directly with customers in deploying Newton to solve real-world use cases. And then we have myself. I will be hosting this session. So with that, I will now pass this on to Laura to move forward with the case for physical AI.
Great. Thank you very much for the introduction, Aristo. Today, I'm excited to make the case that physical AI is the next major frontier. And I'm excited also to share the work that we have been doing at Archetype to make that a reality. So we have all seen that over the past few years, AI and particularly LLMs have fundamentally changed how we interact with the digital world. Whether it's generating code, summarizing research, or automating workflows, these tools are now able to compress hours of work into minutes, and they keep getting better every day. And underlying all of this is a powerful idea of the foundation model paradigm, where one model, which is trained at scale, can generalize across many different tasks and domains. But while the digital world has been deeply transformed by AI, the physical world beyond robotics, say, for example, factories or warehouses or power plants, has yet to have its AI moment. And this is despite the fact that physical industries pretty much run the global economy, where any failure or inefficiency has immediate consequences, often more drastic than anything in the digital realm. However, LLMs, which have dominated the AI conversation as of late, were never really designed for the physical world. They were designed to handle things like text and tokens. But the physical world doesn't really communicate in words or tokens. It actually speaks in terms of much more complex quantities like torque, pressure, electrical voltage, electrical current, and so on. And so the physical world produces a very large amount of complex and structured data, but we have the hypothesis that buried under all those noisy complex signals is actually everything we need to actually understand the systems where they come from. And so the challenge currently is that most existing approaches fall into two camps. On one hand, we have bespoke models, which require deep domain expertise and a long time to deploy, and still only work for one system. On the other hand, we have LLMs, as we have been discussing, that despite their impressive capabilities, were not really designed to handle the continuous but noisy physical quantities that we're working with in the physical world. And so what's needed is a different type of paradigm that realizes general physical intelligence. So what we want is a foundation model that learns directly from physical signals and generalizes across systems and different sensors. So essentially what we're looking for is a model that can understand the physical world the same way LLMs can understand text and language. Now, before I get into our model Newton, it's important to understand why LLMs currently fall short for the physical world. And here it helps to look at what they are actually designed for. So first of all, LLMs operate on discrete tokens, which come from discrete kernels of information, like words, images, image patches, audio units, and so on. And moreover, these are inputs that have natural boundaries and semantic meaning. In contrast, sensor signals are continuous, and they tend to span a very large frequency range that goes from fractions of hertz to several thousands of hertz. And so trying to tokenize them in the same way you would tokenize a sentence will lead to loss of information. Moreover, LLMs also benefit from operating on coarse temporal abstractions, because this is how language works pretty much. So there are words, sentences, events, and so on. Whereas physical systems are actually driven by dynamic processes that unfold at millisecond scales. And then finally, there's the data aspect. LLMs, as we all know, were trained on human language, which is basically like the most structured, best curated data set in history. Whereas physical data, as I mentioned before, is also abundant, but it tends to be very messy, it tends to be unlabeled and noisy, and dependent on the specific device it came from. So the data assumptions that were baked into LLMs do not transfer very well to the physical world. And so if we are trying to build AI for the physical world, that means that we pretty much have to start from different first principles. So what we are proposing at Archetype is to build a foundation model, which we call Newton, which is designed specifically for the physical world. And so the core idea here is that it's the same one that made LLMs transformative in a sense. So instead of building narrow bespoke models for every different modality or system, we aim to train a single model on diverse physical data such that it can develop a general understanding of how the physical world behaves. So the best way to think about it is that Newton is effectively like a kind of ChatGPT for the physical world, such that you should be able to ask it what is happening across your sensor data in real time, and for example, get answers that would have previously required a team of specialists and the bespoke models that I was talking about before. Now, the paper on the right, which we published in 2024, represents one of our first steps in the process of building Newton. Here, we introduce a core physical world model that sits at the heart of Newton. Our model pretty much learns the underlying patterns of physical systems from a large amount of sensor data. And because it's able to learn general physical representations, it's also able to generalize across many difficult physical domains and systems. So how does that work exactly? So we have the hypothesis that every physical system, whether it's a motor, a pipeline, an electrical grid, can be described through time-varying signals. For example, we have temperature, current, pressure, vibration, and so on. So rather than hard-coding physics equations into our model, it actually learns purely from raw sensor measurements with no prior assumptions about the underlying physics. So this is what I was saying before about our hypothesis that the large amount of sensor data that is available already probably contains a lot of the information that explains the underlying systems it came from. So within this framework, sensor observations flow into an encoder, which compresses these sensor observations pretty much into a compact latent representation of the physical process that underlies it. And it actually turns out that this latent representation is really versatile. It can be consumed directly for tasks like classification or anomaly detection, or it can be passed through a lightweight decoder to reconstruct past behavior or forecast future trajectories. Overall, the ultimate goal of this paradigm was to develop a single model for a variety of physical processes, where you train it on a diverse but sparse set of observations of the world, and then you have it generalize to sensors and domains that were never seen in training. And this is actually really impactful because it means that we don't have to build a narrow tailored data set for every single use case we want to solve or build a bespoke model accordingly. Instead, we can learn a broad model that applies to a number of physical domains that were never actually seen in training. And so very briefly, this is the high-level architecture of the model. So it's a transformer-based encoder that was trained on a large cross-modal, cross-domain dataset with almost 600 million real-world sensor measurements. And we trained this in a fully self-supervised way. So there were no human-generated labels, no implicit biases, and generally no human-driven biases or preconceptions. Instead, what this approach allowed was the model to learn a physical representation purely from data. Now, one of the key features is that because the model was trained across such a diverse range of physical signals, it was actually forced to learn the underlying structure of physical behavior itself. And the resulting representations turn out to encode phenomena that make sense to us semantically, which is really interesting. So we can see that the same pre-trained model with no human labels whatsoever is actually able to cluster meaningful groupings of physical phenomena across distinct domains. So take the gearbox example on the left, where vibration data from healthy and faulty gearboxes separates cleanly into two different clusters, or human motion types according to accelerometer data for activities like running, walking, cycling, and so on. And here we see that the embedding space organizes itself into rich, well-separated clusters, each of them characterizing a different physical signature in the domain of human motion. And because of this, we can execute tasks that are working straight out of the box, like the clustering examples I just described, or even things like anomaly detection, where, for example, in this wind turbine example, anomalies are discovered simply by analyzing the geometry of the embedding space. And we can see them here in the orange color. Moreover, as I mentioned before, we can also pass this powerful latent representation through a lightweight decoder such that it can also predict how physical processes change over time, even those that it never saw in training. In this example, the model was able to predict the trajectory of the spring mass system as captured by an accelerometer, even though it never ever saw it in the training data or even accelerometer data for that matter. It is also worth noting that the model was not only able to forecast simple oscillatory behavior, as we see at the beginning of the recording, but it's also able to forecast very complex processes, like this chaotic behavior of an elastic pendulum, which is very irregular and it's very sensitive to initial states. Here's another example with a different physical phenomena. So we took two beakers of fluid, and the temperature differential between them is converted to an electrical current. So what we saw is that the exact same model, without changing any weights, was also able to successfully forecast this underlying physical process. And we didn't only look at fundamental physical experiments. We extended Newton to actually forecast complex real-world processes, such as, for example, countrywide electricity consumption, oil temperature in transformers, water vapor concentrations, and so on. And in each case, we found that Newton, which had never been trained on this data, was able to accurately forecast future trajectories purely from its pre-trained weights. As we can see here, the model even outperforms specialized models trained specifically on the target data. This shows that by training on a cross-modal broad set of data, you can actually induce better understanding of physical processes than training bespoke models on the target data. And so this speaks in general to the power of the foundation model paradigm, where you can leverage this broad set of underlying physics to perform on many tasks across many different domains. Okay, so we've seen so far how the physics world model discovers the underlying structure of physical behavior through a diverse set of direct sensor observations, which, as we saw, enables it to seamlessly be applied to many downstream tasks, even in systems that were never seen in training. Now, let me describe what happens when we combine this physical world model with a semantic component that actually aligns our human mental model of the physical world. So what we do now is that we can use a semantic model to translate the understanding captured by the physical model into human interpretable meaning and insights. From these two components, both individually and in tandem, we can actually now derive any number of use cases, including, as we saw before, things like forecasting, anomaly detection, classification, and so on. And these are all things that live in the physical numerical realm. But we can actually now translate all these physical concepts to rich natural language descriptions, alerts, explanations, and insights, and so on, by connecting these to different components of Newton, the world model that describes physics and the world model that describes the semantic understanding of this physics. And so the powerful thing here is that all of the data that is inputted to both models, both from the physical measurement perspective and the contextual information provided in natural language perspective, are actually combined into one unified embedding space. So they're actually sharing a representation. What this means is that you can very easily interact with the model through natural language to steer it to extract the desired insights and extract the desired information from the physical understanding portion. So here is an example of Newton in action, where we ask the model in natural language to give us some insights on whether there was package mishandling. So what we see here is someone holding a phone, and we use the accelerometer data to simulate a situation where an accelerometer is inside a package. And so, yeah, we're asking Newton, do you think this package was mishandled? Can you give us more information about that? So it's really interesting to see how Newton seamlessly integrates the accelerometer motion signatures with the natural language prompt and context to generate useful insights on the fly. And in this example in particular, we wish to obtain information about package mishandling. But we can request very different insights in a very seamless way, simply by asking the model to focus on something else. For example, is the package now in transit? Is the package being stationary, or whatever other insights we want to derive from this? Now, in this other example, we are now using multiple sensor modalities along with the textual context. And this is in order to do things like interpret fire safety risk and provide recommendations accordingly. So on the left side here, we have a radar, which is actually a fairly complex and non-interpretable sensor modality. And then in the middle, we have audio data. Now, Newton is able to fuse these two together along with natural language instruction and context in order to realize that there is a situation that requires attention because an alarm is going off and someone is present in the room. And then it also provides recommendations on what to do in this situation. And this is really powerful because there was absolutely no pre-programming of all these different types of responses. This is simply the model effectively translating signal to meaning in real time and incorporating the context in a meaningful way. Finally, Newton also understands the physical world spatially. It can identify objects and precisely locate them in specific contexts. So here in this example, we have a camera feed, and Newton is able to correctly identify two people sitting on a bench over here. This is a scene that is really subtle and really requires spatial understanding. And as we can see, other general purpose models still sometimes struggle with this kind of task that is seemingly simple, but actually requires a pretty good understanding of spatial relations. And then finally, this is early work that takes Newton a step further into signal-to-signal intelligence. And this can be done by leveraging the unified embedding space I was talking about before. So what you're seeing here is an accelerometer signal at the top that is fed directly into Newton. And what we do is that we prompt it with natural language to detect to detect signal anomalies. And now at the output, instead of getting a description in natural language, we actually get a synthesized web form that marks exactly where those anomalies occurred. So this is really interesting because now we have an input signal going into the model, and we could have a natural language description as an output of the model, but in this case, we have a signal as an output of the model. And again, this doesn't require any human labeling or customized model. It's just Newton and its capability of reasoning across different modalities. And so overall, we have defined 5 different pillars on how we think we can bring physical AI to production. The first three on the top, namely physical world intelligence, multimodal sensor fusion, and semantic understanding, are properties that we solve throughout the Newton model itself, as we have seen throughout this talk. The model, as we saw, understands time, space, and physics-driven behavior across different sensors and modalities. And critically, it doesn't just detect and predict, it actually explains. As we can see, as we saw before, you can ask things to Newton regarding the physical processes. You can ask things like, why? Can you explain how did this happen? And so on, which is very important. Now, the last two pillars, namely edge native development and data sovereignty, are more about making Newton actually usable in the real world. That is, we wish to enable running inference wherever the data is generated for latency and privacy prioritization. And we also want to have full control over data and models through sovereignty. So that concludes my portion of this webinar. And so I'll hand it over to Lucas. Thank you very much.
That's great. Thank you very much, Laura. Just checking you guys can see my screen and can hear me, right? At least if you can just please confirm. Awesome. Thank you.
Yes, we can. Thank you.
Great. So the main interface that the users have with our model today is our current platform, right? And the platform exists essentially to accelerate the development and the testing of those physical agents. You can also do some kind of custom fine-tuning there if you're working on a very complex behavior or problem. But essentially, once you use the platform to build and to test these physical agents, you want to either deploy it, right, to the cloud or also to the edge. And the platform also has capabilities to help you do that. So you can either deploy to the cloud or to the edge once you have this working agent that you use the platform to build. Um, sorry, I'm just struggling here to change the slide. I don't know what's happening. Just 1 second, sorry. All right, now we have it. And Laura mentioned, right, that the Newton itself is one of its core capabilities is generalization. So you can use Newton across many different use cases. But with our experiment with customers, we realize that even though we are working in many different industries and many different customers, we realize that there are some problems which are kind of common across many of them. And with that in mind, we created the pre-built agents. So today, if you go to the platform, you see 3 pre-built agents, which are essentially agents that are very easy and fast to get set up. But of course, they allow for some level of personalization, right, to your specific use case. The first pre-built agent that we have is process monitoring. And here, the main goal is to identify anomalies, predict failures, and optimize performance in real time when you're working with heavy and industrial machinery. We also have task verification agent, which basically verifies task compliance. It tries to spot deviation and measure productivity in assembly lines and events. And then finally, we have safety and security agent, which basically monitors environments and is able to flag whenever some kind of hazard or unsafe behavior is detected. So as I said, those are pre-built agents, super easy to get set up with. And then, of course, they allow for some level of personalization to each specific problem that you're trying to solve. And now we bring a series of examples in which we used those pre-built agents. The first one is using the process monitoring agent. And here the biggest goal was to detect anomalies in complex wind turbines. We use Newton out of the box here, and the final output here is that it discovered 9 previously unknown failure patterns. So these are patterns of failure which even industry experts were not aware of, and it used more than 40 sensors to do that. Of course, this is a very complex industry, right? And the impact is huge. At the end of the day, that generated more than 50 million in annual downtime impact. So that's a pretty significant use case that one of our pre-built agents solved. That's pretty interesting. Another example of the process monitoring agent that we had was to evaluate performance of HVAC systems. So HVAC is a pretty solid research field, and there are many softwares which are specialized at detecting anomalies in HVAC systems. So what we did was doing some research on this software, and we actually used the outputs from those softwares to benchmark against our out-of-the-box Newton. And the results are also pretty exciting. So our out-of-the-box Newton, which was, of course, as we mentioned, generalizable, has high generalization capabilities, managed to outperform those softwares which are specialized in HVAC systems. So this is another very significant result that we got from the multimodal model, sorry, the foundational model. And I think this Laura also covered the embedding space, right? We are just bringing another example of that, how Newton is able to capture different states and how they are semantically driven into different regions of that embedding space. So this is still on the HVAC use case. Each one of those green dots represent a data point of a normal behavior, and then the red ones represent a data point on an anomalous behavior. It can be cooling valve being stuck, a damper being stuck, or a filter restriction. And the cool thing to look at here is that we see a clear separation in this embedding state. So normal behavior tends to cluster themselves together, and whereas the anomalous behavior also generates some very specific clusters, and the more separation we get from them, the best is the understanding of Newton that they are actually two different states. So that's also a pretty interesting plot. Uh, Let me actually hit play already. Another very interesting use case, and this one, I personally like it a lot because it showcases the multimodal capability. The goal here was to detect anomalies in data center operations, right? And if you have access, for example, to a single sensor, to a single source, let's see, for example, the temperature here changing over time, as we see in the chart, you would very likely flag that there's some kind of anomaly once that temperature drops, right? But what happens is Newton not only has access to the temperature variations, but it also has access to the video footage of that environment. And then when you're prompting it in natural language, it fuses both of those inputs together, and then it's able to come up with way more accurate and complete outputs, right, of what is actually happening in that environment. So it's not just about flagging, hey, there's a big drop in temperature, but it's actually reasoning and comparing the drop in temperature with the fact that there's someone walking through the room and then opening the door and actually interacting with that environment, which very likely cause that drop in temperature. So as I said, that use case is great to showcase this multimodal sensor fusion capability. This is now an example on the task verification agent. Imagine that in one side you have a list of everything that needs to be accomplished in a specific assembly event. And then in the other side, you have video footage of someone actually trying to perform those steps. And then Newton will have access to both of them, right? The list and also the video. And then this thing becomes essentially a comparison exercise. So Newton will look at the list, it will also look at the video and try to understand whether the worker is actually performing every step that is described in this list. And then, of course, if there are any kind of deviations from what is being done to what should have been done, Newton is able to flag that as well. So I think it's clear that this kind of capability is super useful when it comes to, a huge assembly line and this kind of tasks. That's another very interesting use case. If I'm not wrong, I think this is the last one that we have to showcase. And it's also one that shows very well the multimodality of the inputs, right? The sensor fusion capability. Here, the biggest goal was to monitor pedestrian safety. And not only Newton has access to the cameras that were installed on top of the traffic lights, but it also had access to the system of the traffic lights itself. So the time series data with how that thing was operating. And then by combining both of them, not only it was able to tell real accidents that happen, which is kind of standard, right? But by combining those two inputs, it was able to flag some kind of almost accidents or some kind of dangerous crossings. So at the end of the day, given that you're looking at those two systems together, you're able to provide way more valuable feedback to the company or to whoever is managing that traffic lights. Uh, one very important thing that I would like to comment on that specific use case is that it was deployed at the edge, and then it's very hard to deploy a 7 billion model to the edge, right? So when that happens, a distillation process is needed. For that specific use case, the model went from 7 billion parameters to 1 billion parameters, so that's a 7x factor in reduction. We can see here in the left-hand side that inferences got faster, right? From 48 to 60% faster. And that had absolutely no impact on performance. So this is the exact result that you would like to see from any kind of distillation process, right? You want to minimize your model as much as you can, keeping the original performance that you had. And that's what happened in this use case. And as I mentioned, this kind of behavior is extremely important to make sure you can run those models, you can run Newton in the edge. I think I think that was it from my side. I'm gonna invite Aristo back,
Great. Thanks, Lucas.
please. Thank you very much.
Okay, so now we can actually head into the Q&A section. So I've been monitoring the Q&A uh, feature here and some of the questions. Please feel free to continue to submit questions and we'll just go through as many as we can. This first one, Laura, is a question about Newton and how Newton and the foundation model approach compares to traditional machine learning.
Yeah, so that's a really good question. I think the main difference is what I said at the beginning of the talk, where Newton has been designed as a foundation model. So what we do is that we train Newton on a very large set of data in order for it to generally try to understand the physical behavior in the real world. Whereas in bespoke models, we would take data from specific domains and train those specific models accordingly. With a foundation model paradigm, the advantage is that by having a single model that generalizes really well, you can apply it to all those different use cases, as opposed to having to build one specific model at a time. And that also improves like the time it takes to actually realize applications from scratch. Whereas in the case of traditional ML, yeah, we have to begin from scratch every single time we want to address a new use case.
Great, thank you. Actually, Laura, one more question for you. What do you see as the tax token equivalent in the physical world?
Yeah, so that's a very good question. I think the honest answer is that there isn't really an equivalence because when it comes to tokenization in language, this really relies a lot or leverages the fact that language has very natural units of meaning. But the closest equivalent is actually what we do in the physical world model, where we take a time series signal and we generate patches. So we kind of generate little portions of a longer time series. And then we take those patches and we map them to the latent space. So I would say that's the closest equivalent of the tokenization.
Great, thank you. And another question, Laura, actually, we hear that failure data is or can be rare in physical systems. So what is your approach? What is our approach to handling that?
Yeah, so this is a really important problem in the physical realm because most of the time we will have data that is really unbalanced. meaning most of the data that we have will belong to one specific class. So when it comes to failure modes in particular, most of the data we will have will be from healthy systems. And so the question is like, how do you address the data imbalance? But actually, as we saw before, our approach is that we don't really use labels when training the physics foundation model. And in fact, what we do is that we let the foundation model just learn on the available data. And what we saw is actually that the anomalies, in a sense, which are very scarce in the real world, just then reveal themselves, not because the model was trained to recognize them explicitly, but just because they fall outside of the structure of the learned embedding space or the structure of the normal behavior. So in a sense, like kind of they reveal themselves through the geometry of the embedding space.
Great, thank you. Let me actually skip around. I'm going to grab a question for Lucas. Um, Lucas, there's a question here around Newton's ability to support zero-shot inference. So maybe can you speak to our ability to handle that, and also how or if we need to handle fine-tuning?
Yeah, this is also a great question. So I think I can speak in two levels, one being from the model perspective and one seeing from an empirical perspective of what we have seen with from customers. I think Laura mentioned many times, so the model was trained on a large set of data considering many different sensors. So it's natural to expect the generalization capability, right? Actually, the experiments that she showed show exactly that the model was able to replicate or to understand behavior of different systems, even though it was not seen in training data. So that's one. There's a second thing, which is what we are seeing with customers, and I think from a 90 to 95% of the use cases that we've been working with, fine tuning was not required at all. So out of the box, Newton was already able to understand the behaviors that we wanted to model on each one of those use cases. And I think that also makes sense to the way that the model was built and trained. I would say that fine tuning is required when you want to capture a very specific behavior and a very complex behavior. So when that's the scenario, then fine tuning is recommended. But overall, Newton out of the box is already doing a great job.
Great, sounds good. Thank you, Lucas. Okay, let's go back to the question list. So, Laura, a question here on video. Can video input be interpreted as sensor data in the physical world model, or is it just being handled through the semantic world model?
Yeah, so currently we're handling it as part of the semantic model, simply because video data, image data in general, has a pretty well-defined structure in a semantic sense. However, I think we can also process it to input it to the physical world model and obtain different types of insights accordingly.
Great, thank you. There's actually one question here. Maybe Lucas, you can comment in here about deploying at the edge and if there's any specific compute requirements. I think Lucas showed a slide at the end about deploying to monitor pedestrian safety. I believe in that case we were able to distill down to that 1 billion parameter model, which I think required like a 2 gig RAM GPU. But we also have a range of models that can even go down to under 100 million parameters. But curious, Lucas, if there's anything else you want to comment on edge compute or requirements around that.
Yeah, I think you were very accurate, Aristo. So there's a very big range. And of course, it comes down to being able to balance the accuracy that we want, so the performance from the model that we want, to the requirements of the box and the use case itself, right? So I think the best answer that we can give here is there is a big range, and then we get a little bit more specific once we have clarity on what's the performance and what is the hardware that the model will need to run on.
Great, thank you, Lucas. I think we just have time for one more question. So this one is for you, Laura. What are the biggest obstacles or challenges that you see to getting to that chat GPT moment for physical AI?
Yeah, that's a very good question. I think this is something that we discussed at the beginning of the presentation. So namely, the main challenge in the physical world is that even though we do have very large amounts of data, most of that data is actually very noisy. It also evolves over time. So in a sense, it's harder to be able to train a model with this very unstructured data. So before the foundation model paradigm, this would require a team of experts to really be able to understand what's going on in this data with like people with domain expertise. So I would say the main challenge is to be able to come up with paradigms that can support this kind of complexity that the physical world data comes with. Yes, I would say that's the main thing to address.
Okay, great. Thank you so much. So with that, let me just share my screen one last time. Okay. Well, thank you for that, Lucas and Laura, for answering those questions. Before we finish, we just wanted to call attention to a new 10-week design fellowship that we have here on the bottom right of the screen. We're launching this design fellowship for students that want to explore the fundamental questions around AI and the physical world. So if you're a student on the call or you know a student interested, please apply. You can use that QR code to get to the job description, or of course, go to our career site to hear more about it. As a reminder, we will be sharing a recording of this session through email in the next day or so. And lastly, please connect with us. Find us on LinkedIn, find us on X. You can go to our website. We'll be doing more of these sessions. So if you follow us, you can stay up to date on the latest. So thanks again for joining the webinar, and thank you to both Laura and Lucas for your help in presenting.